All right, team, ladies and gentlemen, hey, welcome to this webinar where I'm going to be talking about the difference between a FMEA and FMECA. And of course, there's a bit of assumed knowledge to an extent implied in the title. But for those who've never ever heard of either of these two, can't even spell FMEA or FMECA, um, we'll go through from scratch about what this is all about. So, for those poor old veterans of my previous, feels like 3,000 webinars, I'm going to use my old faithful smart lock as the example for today's conversation. Now, what that means is that we need to look at this as something we are trying to make good. FMEAs and FMECAs are often seen as something you just do, but the main point of a FMEA and FMECA and/or FMECA is to make something good, reliable, robust, efficient, whatever the right term is. And of course, with something that you're about to design from scratch, you might not know exactly what the final design will look like, but there's no reason for you to not have a pretty good idea, like what you can see on the screen, about what your thing is going to look like. So here we have 17 different components, 16 of them are different because two of the handles are identical. We know that before we design a smart lock, this is what it's going to roughly look like. We know these components and these subsystems will exist. And of course, if we were to zoom in on a very important part of our smart lock, you can see the electric motor here, which is connected to the PCB via two wires / two cables. We are looking at the heart and soul, so to speak, of our smart lock. Now, many great ideas, really sophisticated, clever designs for emerging electronic consumer products have come unstuck because people forget the basics. And the basics that I often use as an example are the effects that door slams will have on these poor old solder joints that connect the cables from the motor to the PCB. Solder joints are not strong. Their main role is to allow the conduction of electricity. And yes, they offer some support or some strength because they retain the conductive cable to the devices, but solder joints have been the undoing of so many really good devices to the extent that many bankruptcies can be tied to not thinking about simple things like solder joints. The idea is that before we want to start designing our amazing smart lock with all that functionality that we can think of, we want to make sure our first design is a robust and reliable design by making sure, for example, we include corrective actions like having thicker gauge wires provide more contact area with the motor's terminals, makes it that connection stronger. Corrective action number 2 is to have shorter wires that accumulate less momentum. And so when that door slams, you don't have a really long unsecured cable yanking with shock forces on the solder joints at each end. And then we have corrective action number 3, where we actually have wires clipped to the chassis of the smart lock, which means that any shock forces or the majority of shock forces are transferred to the chassis and not the solder joints. Another corrective action is to have a socket and plug instead of a solder joint in the circuit board, which happens to also make assembly so much easier. And so these are examples of corrective actions that, bear with me with this one, are essentially fast, simple, and free. Now, before people get irate and say, no, they're not all free. If you use socket and plugs instead of solder joints, that comes at an additional cost, and you're not wrong. But in terms of the relative cost with respect to the total production cost for a single smart lock unit, these are trivially insignificant costs. And these trivially insignificant costs, which have virtually no impact on profit margins, mean that when the decision is made to consider these corrective actions, they should be absolutely allowed to be, or demanded to be incorporated into our first design. But of course, they only remain fast, simple, and free if they are embedded within our first design. If you have 16 design reviews and you're 3 months or 3 months away from launch, and you say, you know what, we need to change our cables connecting our motor joints to our PCBs so that we now have socket and plugs instead of solder joints. Well, now you need to almost undo and then redo a good chunk of your design work, and that's where the costs mount up. So if you do it, and you do all this stuff or incorporate all this stuff in your first design, then it's fast, simple, / free. And so what this means is that if we are able to think about all these little things early in designs or before our first design, we make reliability happen from the start, which is sounds intimidating to many because, of course, there's hundreds of, perhaps thousands of different ways your yet to be designed and manufactured product can fail. And of course, we can't sit down and go through every single one of those and in a meaningful way. If everything's important, then nothing's important. Enter FMEAs. FMEAs are really, really powerful at helping us understand what it is we need to focus on, not just with smart locks like this, or products like smart locks, I should say, but with the manufacturing processes that make these things. But a FMEA is actually a group activity. Now, many people or many textbooks will say, well, FMEA is all about doing this with these definitions, you have these tables, these outputs. No, always think of a FMEA as a group activity that contains 4 to 8 people who are cross-functional representatives, not interns, not the people who drew the shortest straw, the respective leaders of different parts of the product design. At the front of the room, we have the facilitator. Facilitator is obviously very, very important. A good FMEA means you've had a good facilitator. And then you have the scribe. For example, over here on the left-hand side, I actually like having at least 2 scribes in the FMEAs I facilitate, because we want to keep the pace going. And one of the reasons I want to have at least two scribes is because one of the things that you often hear when people say what a FMEA is this thing called the FMEA worksheet. The FMEA worksheet is essentially the thing which summarizes those wonderful ideas that lead us to coming up with those really fast, simple, free corrective actions in a prioritized way. So we're not trying to fix everything. We just want to fix the simple things that are going to have the biggest impact on reliability and quality as quickly and cheaply and efficiently as possible. And so having more than one facilitator can, more than one scribe can make this really, really helpful. But it comes down in many ways to the FMEA facilitator, him or herself. And when I say the FMEA facilitator, I mean the amazing FMEA facilitator. And so those group activities can happen any stage of the production life cycle. In fact, there's different types of FMEA activities that occur in the production life cycle or the development life cycle. And here is a generic development life cycle we can see on the screen. And it's deliberately high level and deliberately non-technical because there's so many different industries with their own different takes on how you go from a great idea to building something in the real world. So you can see we have this light bulb on the left representing that great idea, and then we move through a concept, specifications, where we more clearly define what our concept needs to be, then design and build, sustain and dispose. And of course, design and building, especially if you include prototypes, is iterative. We go through many attempts to design something, even if the first few attempts are in our brain when we're a junior engineer or designer or a technician who's coming up with their way of solving a problem. We inherently, as human beings, will go through different options in our brain. So it is an iterative process in our brain, even before we start doing anything on paper. The first type of FMEA, the first type of group activity that I want to talk about is this thing called the system FMEA. Now, the system FMEA is conducted on 100% of the system or your product or your smart lock. And because it's conducted on 100% of the system, it is high level, which is okay. It's high level with analysis focused on system-specific issues. And so a system FMEA will include conversations that revolve around things like the human-machine interface, which affects customer experience. It'll also help us describe failure severity, including issues that impact safety. The reason why a system FMEA does this is because severity is all about the impact it has on the user / customer / the systems around it. And so at the highest level, this has to happen at the highest level. We're trying to understand what happens to things outside of our product or system. The other thing the system FMEA helps us out with is understanding the interfaces between components and other systems / subsystems within our product or system. The reason why this is very important is because about half of all failures occur at interfaces. Just ask the European Space Agency and NASA. The overwhelming majority of those probes and spacecraft failing over the years have been because simple things like the European Space Agency has software code which outputs torque readings in terms of Newton meters, where NASA software or hardware subsystems and elements are expecting torque inputs in terms of foot-pounds. So the classic interface error. Both components / subsystems are working perfectly fine as they are defined to work themselves, but because there is an issue between how those two interact, we have a failure. And so it's a really easy way to drastically improve reliability by thinking about interface failures. The other thing that system FMEA has helped us out with is maintenance and support strategy. And that's very important even for things like smart locks, which don't get serviced or don't get sent back to depots to be overhauled or things like that. But smart locks contain software and firmware, and they need to be maintained over the life of the product, including security stuff. And so pretty much everything we build these days has some form of maintenance and support strategy we need to get on top of. And depending on what the user is expecting, we need to design something which aligns with their expectations for what their role needs to be in maintenance and support. The user of a smart lock just wants all these firmware and software updates to happen without them having to do a damn thing. And so it's very important to understand what it is our maintenance and support strategy needs to be. Another thing that system FMEAs are incredibly awesome at is working out if we have missed any requirements or specifications. We often get handed a huge Excel spreadsheet with temperatures and speeds and times and everything else, but often we forget about some really simple things, and having a system FMEA group activity can help us work out, hey, that smart lock actually needs to have a motion sensor installed or as part of it, because we have worked out that we need to have our keypad illuminate at night. And that only works when the smart lock knows there's someone nearby. So we just worked out we've forgotten an entire component for our product. Okay, let's go and fix that right now. A long story short, but above and beyond all those things, a system FMEA helps us out prioritize our effort and focus on the vital few. And so we're not getting down into the weeds just yet in terms of designing our smart lock. It's all about the high-level understanding of our thing before we start designing it, which leads us to the next type of FMEA we want to do, which is the design FMEA. Now, design FMEAs only get done on parts of your system, i.e. the high-risk elements of the system, the vital few that were identified as part of your system FMEA. Now, one of my favorite movies of all times is The Incredibles. And you might remember, I don't remember the name of the bad guy in the first one, but he was railing against superheroes. He didn't like the idea of superheroes because he wanted to feel super. And so when he was rejected as a young child by Mr. Incredible, his life mission was to essentially eliminate superheroes across the world. And also and one way of doing that was killing them. The other way of doing that was making sure he created technology which allowed everyone to have superhero powers. And the reason why he was doing that is because he said if everyone was super, then no one would be super. That means no one is better. No one has specific skills that no one else has. Same thing with importance. If everything is important in your system, then nothing's important. So you only want to do design FMEAs on the high-risk elements of your system. And these are now done by smaller, distinct groups or teams responsible for different parts of the system. And so the design FMEA gets done at the very start of the design process, where you start really formulating how your thing's going to look like. And so, for example, here's our design FMEA facilitator. And this guy is the design FMEA facilitator for the printable circuit board. Now, this might be the head of the electrical engineering team. And the reason why he now needs to do a design FMEA is because the system FMEA identified that the printable circuit board was one of the troubling parts of the system. You know, a lot of concerns about how the printable circuit board is going to contribute to potentially high failure rates. Essentially, this was a part of our system that was keeping up the people at night when it came to concerns about robustness and longevity. And so they decided that, hey, we'll do a design FMEA on the printable circuit board. And so what that means is that this gentleman with his electrical engineers or the right people will come up, conduct his own design FMEA, which is distinct and separate to the system FMEA. And they might identify, for example, 19 potential root cause statements, i.e. ways that 19 different high-risk ways the product might fail, and prioritize perhaps 4 corrective actions for those 19 potential root cause statements to incorporate into the upgraded design of the team's PCB. And as a result, the facilitator can say, we are now very proud of our final design. So the idea is that you only do a design FMEA on the subsystems or components where you have issues or concerns, and the outcomes or the outputs of a design FMEA are those corrective actions we looked at earlier in the this conversation. Those, remember those, we looked at the issues where those solder joints might fracture if our smart lock is part of a door that is slammed repeatedly. And so those fast, simple, and usually free corrective actions that we can embed into the first design. Those corrective actions can be not just design changes, but they can also be the recommendation to implement a DFR activity, design for reliability activity, or change a guidebook, or use design guidance, or look at what we've done in the past. If you don't know what the weak points of your PCB are, for example, vibration, then a corrective action might be to conduct highly accelerated live testing to try and find those weak points and design them out of the system. So the corrective actions really target our efforts to the vital few ways our vital few subsystems and components will fail. And the other things that design FMEAs can influence include system and component test plans. We get a good understanding of the vital few dominant failure mechanisms, which means we can now model reliability based on those dominant failure mechanisms. We conduct accelerated life testing to quantify the life of our product based on those dominant few failure mechanisms. Long story short, we are all about improving the design for our design FMEAs. Now, a lot of people say, oh, okay, so if you're only doing design FMEAs on 4 components of your smart lock, does that mean you're forgetting about reliability for the rest of the components? The answer is absolutely not. It's just that for whatever reason, we believe that those other components are low risk enough that we only need to rely on the good engineering judgment of the respective design teams to make sure that component is reliable. The keypad, for example, we might be comfortable enough that that is such a mature technology that as long as our keypad design team follow well-known practices for designing reliable keypads, we're going to have a reliable keypad. If we can't say the same thing about a PCB, then the PCB might be a candidate component for a design FMEA. And so we're never discounting reliability for things we don't conduct design FMEAs on. It's just that we are comfortable that we have the requisite skill and expertise to make those things reliable enough. We only focus on the vital few weak parts or perceived weak parts of our system. And so that's what design FMEAs are all about. Now, this is where people make a mistake, or people can make a mistake. And that is where you discount everything I've just said and try and do design FMEAs on everything. You know, like I said, if everything's important, then nothing's important. And so if you try and, instead of just doing design FMEAs on the few components that are going to keep you up at night, you try and do design FMEAs on every single component, essentially that means that you exhaust your organization. You want to, like I say, rely on engineering judgment for low risk elements of your system. And if you don't, you just trivialize the FMEA. You exhaust everyone. And also, the FMEA doesn't make the design better because we're just trying to get through it. And everyone now essentially switches off thereafter. So your FMEAs stop looking like a really productive effort and start looking like this, where you have a single dominant personality just trying to scribble as many ideas about what can go wrong as possible into that FMEA worksheet. It just never works. You want to focus on the vital few things that are going to keep you up at night. And so if we go back to the idea where we have design FMEAs conducted on a small number of your components or subsystems, then some people ask me, well, what if my item, what if my smart lock equivalent is actually small or simple? And beyond that is perhaps not high risk. We don't have inexperienced staff. The people we have in our organization have been designing this sort of thing for years, and our product is not developmental. Maybe it's an incremental improvement from the previous generation of our product. Then it's okay to combine your system and design FMEAs into a single workshop. But you shouldn't just do this to try and get it over and done with. You should only ever do this if your item is simple, not high risk, don't have inexperienced staff, and it's not developmental. This is a more efficient way of doing it. But if your item is complex, if it does involve risk, if your staff are inexperienced or it's developmental, then investing more time and effort into distinct system and design FMEAs is what you absolutely might need to do. And so a system FMEA, if you're going to separate these two activities, will help you work out what components you need to do your design FMEA on. Now, I need to talk about this other activity, which we call a criticality analysis. I can see a couple of questions and comments coming through, where Johan says, what do you say to a customer who wants to see a design FMEA on every component? We're going to come back to the one in a minute. And Sanjeev writes, a smart maintainability KPI is key. I think you're just making a comment about what I said. And Carl said a maintenance strategy is a comprehensive blueprint for how companies minimize downtime, keep maintenance costs at bay, and ensure their factories work at or near capacity. Any thoughts? Well, I concur with that for a very specific type of organization. But of course, maintenance strategies are used by people who own fleets of trucks, and maintenance strategies are used by landscapers, etc., etc., etc. So maintenance is all about making sure your stuff works when you want it to work. And of course, there's a more technical definition than that, but hopefully for this conversation, that'll suffice. Samantha writes, if we have a first of a kind system in an entirely new environment, how do you recommend narrowing down our priority components? The system FMEA is perfect for that. The system FMEA conducted at the highest level. In essence, the corrective actions from system FMEAs will include the vital few subsystems or components that you need to focus your design FMEA effort on. So system FMEAs are just absolutely brilliant at doing that, especially when you don't think you have a lot of information. In the real world, we actually do have a lot of information. It's just that subjective stuff in our brains we call experience and corporate knowledge. That's incredibly valuable and we shouldn't waste it. And so if you are doing something for the very first time, a system FMEA is very helpful. And Sanjeev writes, at what stage do P FMEAs start? And I'm going to come back to that one as well. So coming back to this brand new activity I introduced, the criticality analysis. Now, criticality analysis is traditionally conducted on 100% of your components or your system. And if you want it to work, it has to be separate to your system and design FMEAs and be done incrementally throughout the design, prototype, production of your thing. There's no way around this. Now, why is this the case? Well, for starters, there is no broad agreement on what a criticality analysis looks like. So of all the standards that are frequently cited for FMEAs and FMECAs. Now, FMEAs, failure modes effect analysis, are different, at least semantically, to failure modes, effects, and criticality analyses. So that apparently, the only difference between a FMEA and a FMECA is that there is a criticality analysis in a FMECA. Problem is, there's no broad agreement on what that criticality analysis looks like, despite what people say. So, for example, these three standard documents will tell you that a FMEA is all about analyzing the risk of each failure mode, where the criticality analyses prioritize each failure mode. That's what these three standards say. These other three standards say that there is no such thing as a criticality analysis, and a FMEA is simply analyze the risk of each failure mode and also prioritize each failure mode. So what that actually means is that depending on which standard you want to choose, an activity where you analyze the risk of each failure mode and then prioritize them for corrective actions is either a FMEA, depending on which standard you want to read, or a FMECA. So technically, they're the same thing. But a lot of reliability professionals will say that they're very, very different. A FMECA conducted in concordance with those first three standards is principally or philosophically identical to a FMEA conducted in accordance with these three standards. And the reality is the standards actually line up pretty well with actually what you're supposed to do. And so we waste so much time talking about this distinct separate criticality analysis as if it's some sort of alien thing, which makes one thing a FMEA and one thing not a FMECA. But there is for whatever reason, a perception on what a criticality analysis is. So let's talk about what a criticality analysis is, even though the standards are very clear about what it does not have to be. And that usually applies to organizations who do want to characterize every possible root cause statement, ways your things can fail. So Samantha, don't worry, those standards are in the workbook that Fred has shared. But just to be clear, those three standards that you asked me to repeat are the Apollo Program Procedure, NIL Standard 1629 Alpha, and IEC 60812. So let's go back to those organizations who do want to characterize every possible root cause statement in terms of failure rates. And because there are some organizations who do want to do this for various reasons, that for whatever reason, this approach, this thing here has been now referred to as a criticality analysis. And so that's what a lot of people think a criticality analysis is, where you investigate every single failure mode or failure mechanism with a failure rate associated with how often that thing's supposed to occur. So FMEA versus criticality analysis. FMEA is always about focusing on the vital few, where a criticality analysis covers every root cause of potential failure. FMEA prioritizes severity, occurrence, and other selected criteria, and criticality analysis only involves numbers associated with severity and occurrence only, as in terms of this is how people perceive it to be. FMEAs are perceived as qualitative ranking of criteria, where criticality analyses are perceived to involve strictly quantitative measuring of occurrence based on failure rates. Just so you know, every single standard says a criticality analysis can be based on subjective assessments and does not have to be based on failure rates or hazard rates. But for whatever reason, most people who do criticality analysis swear by this being swear by this definition here, where you have to base it on occurrence and failure rates. For FMEAs, the objective is to rapidly identify corrective actions, where criticality analyses, as a rule, are used by organizations to inform support systems, logistics, and maintenance regimes. Often those organizations who demand a criticality analysis using failure rates or hazard rates are actually demanding those failure rates and hazard rates to inform things like the amounts of spare parts they need to have, or the amount of tradespeople, technicians, maintainers they need to have. And so a criticality analysis, in terms of how it's perceived today, has a lot less to do with reliability and a lot more to do with supportability or logistics or maintenance. And so for that reason, a criticality analysis has to be done distinct from those system and design FMEAs. They're all about those. The system design FMEAs are supposed to be done early and relatively quickly to come up with great designs, where the criticality analysis is based on analyzing what that final design looks like in terms of every possible root cause of failure, every failure mode, which is ranked on a combination of severity and other risk factors like likelihood. But you can only ever understand every failure mode once you complete design. You can't possibly predict every single failure mode at the start of design. And like I said, a lot of people tend to use failure rates for this perception or this interpretation of what a criticality analysis is. And so criticality analyses are all about predicting the effects of failure for your system as designed to help inform the maintenance strategy, to help inform sparing, and to help inform logistics. Now, this only matters to organizations who have highly proceduralized and formalized support systems, not the manufacturers of smart locks. So let's look at how criticality analysis might work for a turret positioning system. Why a turret positioning system? Well, here's a turret positioning system. You know, people might be looking at this thing going, what on earth is that? Well, this is a system which exists inside an armored vehicle used by military, which has lots of procedures and formalized support structures. You can see there's a big ring in the middle. That's called the turret ring. And that's because this ring is bolted to the turret of something like a tank. And those, you can see two electric motors or rotary gear drives each side of this turret ring. And these motors are, you can see, able to twist and turn this turret ring. So long story short, those motors control where the turret is pointing in terms of left to right. You can see a component right in the middle of this turret ring, which looks a little bit weird and lonely. That's called a linear drive. And that essentially involves a piston or a cylinder which goes up and down. So you can imagine a tank with a big main barrel for its cannon. That linear drive in the middle pushes barrel up and down so that you now can control where the turret is pointing from left to right, or where the barrel of that weapon is pointing from left to right, and the elevation of that barrel. So you can now have this barrel pointing pretty much anywhere. You can also see there's this weird little box, sort of round arrows next to the rotary gear drive on the left. That contains 3 gyroscopes. And those 3 gyroscopes are connected to a computer at the bottom left, as are the hand controls, which look like joysticks. And the idea is that when you have your tank traveling at high speed, going through gullies, going over boulders, turning left and right around trees, these gyroscopes will automatically work out how that tank is traveling and adjust the turret and the barrel of the tank to make sure that no matter what the tank is doing, the barrel keeps pointing in the right direction, in the same direction, until the gunner who controls the barrel provides inputs to make that barrel change direction, change its point of aim, I should say. And so the turret positioning system is a very important system within tanks and other armored vehicles. So a criticality analysis is conducted in every part of a turret positioning system. So let's focus on one specific component of this turret positioning system, the rotary gear drive. 2 of them, which are essentially, what's that happening there? The rotary gear drive, which is a big electric motor, which is obviously very, very important. Now, from previous, those who are been involved with some of my previous lessons, you know that I've gone through root cause analysis, where you ask yourselves a bunch of questions going from the top to bottom to work out what the root causes of failures are. So for the criticality analysis, when you're doing a criticality analysis for real, the first question you ask about components like the rotary gear drive is, what might my component not do / not do to constitute failure? The answer to this question is a functional failure mode, the functional consequence of failure mechanisms. So for example, a functional failure mode could be the shaft of my rotary gear drive won't turn at all. Another way our thing can fail is the maximum shaft speed is below 180 RPM. It still failed because it's supposed to be able to exceed that speed, but it's now got some level of degraded performance. Still a failure, not nearly as bad as not being able to turn at all, but a failure nonetheless. Another example of functional failure mode is the noise exceeds 25 decibels, which is the obviously required maximum noise level for our rotary gear drive. And you can see that each one of these pie slices around the rotary gear drive represent a different functional failure mode. You're going to see why we have these pie slices and why these slices have different sizes. So here are the functional failure modes for our rotary gear drive. Now, for criticality analysis, you need to then look at each functional failure mode and then ask yourself, okay, for that particular functional failure mode, if I was to pull my rotary gear drive apart, if it did fail with any one of those functional failure modes, what would the broken bit look like on the inside? The answer to that question is a physical failure mode. So a physical failure mode is a physical consequence of failure mechanisms. So for example, if we're examining a potential failure where the maximum shaft speed is below 180 RPM, there are a number of different things that could be broken in our hypothetical potential failure scenario should we pull our rotary gear drive apart. You can have a damaged capacitor, winding insulation degradation, molten winding insulation, delaminated heat transfer pad, failed bearing, etc., etc., etc. So now we have 5 different physical failure modes which might result in a functional failure mode where our maximum shaft speed is below 180 RPM. But we're not done yet because we need to go down another layer, because for each physical failure mode, there are more slices to this pie. If we were to, in our potential failure scenario, if we were to look at that scenario in question, pull our hypothetical rotary gear drive apart, see what the broken bit looks like, the next question we need to ask ourselves is, how did it break? The answer to that question is a failure mechanism. So a failure mechanism is a physical, chemical, electrical, thermal, or other process which results in failure. So for one particular failure scenario where the maximum shaft speed is below 180 RPM due to winding insulation degradation, there are 2 potential failure mechanisms that could cause this, at least in our mind. One is corrosion and one is plastic deformation. And so you can see we have 2 more slices of that pie for that failure scenario. And so they're the failure mechanisms. You can see that the slices of pie are starting to become quite numerous, but we're still not done yet, because for each failure mechanism, something has to start it. So what's in each one of these failure scenarios, the things that start failure mechanisms are what we call faults, the immediate causes of failure, the circumstance that allowed the corrosion or the oxidation or the dendritic growth to occur. So go back to one failure scenario where the maximum shaft speed is below 180 RPM due to winding insulation degradation caused by plastic deformation. Big breath, because it's quite detailed right now. The 2 faults that we envisage would cause this particular failure scenario could be contamination or excessive torque used during manufacture in terms of securing things. I can see Carl writes, criticality analysis is a systematic approach to evaluate and prioritize assets based on the severity and likelihood of potential failures. Any thoughts? I'm not sure how to answer this question apart from saying this entire webinar contains my thoughts on what criticality analysis is. So yeah, if we keep listening, maybe you can get a good idea of what my thoughts are for that definition of criticality analysis. So criticality analysis, as is routinely perceived to be the way we do things, where we demand failure rates to be used to create a document or create an output which we classify as a criticality analysis. We, as a rule, when you taught how to do these criticality analyses, you're asked to estimate the final failure rate of your component in question. You're then asked to identify this failure mode ratio for each particular root cause statement, i.e. failure scenario. So we often use the letter alpha to represent the fraction of failures caused by each different failure scenario after you've implemented corrective actions. And then we also have this other others characteristic here, or the others parameter, the failure effect probability for each root cause statement, i.e. if that failure scenario occurs, what's the probability of systemic failure? So, which is difficult to easily explain, but there are some scenarios where components can fail and might not always cause systemic failure. And that often does apply to things like tanks, where you are not going to be using your turret and your barrel for every single mission. So perhaps you might use the beta parameter or beta estimate here to characterize the percentage of missions you think an out of action turret positioning system might affect. And sometimes you'll see FMECAs or criticality analyses, which includes an environmental factor, where you just have a guess based on how harsh you think the environment is. And if you think the environment is harsh, then you might have an environmental factor of where K is equal to 2. Essentially, all that does is double the perceived failure rate. There's no science behind it. It's just a guess. And then you have all these different characteristics or parameters or estimates for every single failure scenario you're supposed to envisage. Now, the reality is I rarely see criticality analyses which come anywhere close to capturing every possible failure mechanism or failure mode for a product, component, subsystem, what have you. You can see here with this rotary gear drive, the number of different slices of pie, which is not unusual, is quite extraordinary. There's over 100 different failure scenarios just for the rotary gear drive, but I rarely see criticality analyses for components of similar complexity genuinely represent all these 100 foreseeable failure scenarios. But this is what a criticality analysis, as perceived to be, is supposed to incorporate. You can then use those numbers to create criticality numbers, which is what we often demand of a FMECA worksheet. So, for example, we looked at the in the rotary gear drive shaft. You just saw how many different functional failure modes, how many different failure scenarios we came up with. So you're about to see a really small summary or excerpt of that little effort on the previous part of this conversation. Let's just say that instead of having over 100 root cause statements or potential failure scenarios, let's just say we only had 3. Now, all I'm doing here is trying to make this simple and fit on the screen. So let's just say we have 3 failure scenarios that we came up with. Of course, way more than this, and we'd expect to have way more than one root cause statement per component. So let's just say these 3 failure scenarios, we need to first have a guess or estimate the failure rate of our rotary gear drive, lambda subscript P. So this is the failure rate for a rotary gear drive. We then, if we want to include an environmental factor, that's where it goes. So we put a 1.25 there because we believe the environment that our turret positioning system is going to be harsh, and you can't see the air quotes, the inverted commas I'm using at this end. And so we just guess 1.25. Sometimes you'll throw in things like operating cycles, because things like turret positioning systems aren't used 100% of the time. So you might have some way of trying to incorporate a mission profile to say, okay, for every mission, our rotary gear drive will spin on average 2,550 cycles. The failure mode ratio, that alpha, okay, you see how these need to add up to 1 for each component. Now remember, if we're being legitimate about this, you'd expect for quite a sophisticated, large electric motor like the one we looked at in the previous slide, you'd expect to have over 100 different failure scenarios, and each one of these 100 failure scenarios needs to have its own failure mode ratio. They need to all add up to 1 for a specific component. But let's keep going, because the next thing we do is then have a failure effect probability where, for example, if the system may not experience failure symptoms if your component fails, and you can incorporate it here. So in this case, you can see that there are failure scenario where there was too much gear noise due to misaligned motor mount. The failure effect probability is 0.15, because that's, again, a guess of the probability of failure for each root cause statement at the system level. Oh, if you can keep up with me, well done. Let's keep going, though, because this is hard work. Then we have the failure mode criticality number, where you simply multiply all the numbers in the rows, and you multiply all those numbers in the rows on the left-hand side. You can see how we're doing that for the first number. See how we're doing that for the second number. See how we're doing that for the third number. So each failure scenario now has its own failure mode criticality number. And then you can often give your entire component a criticality number. And these are simply the sum of each failure mode criticality number. And depending on which standard you look at, a bunch of different ideas for what you do with these criticality numbers, noting that you sort of eliminated the ability for us to easily incorporate severity, because it's incorporated with the failure effect probability. But you might then plot these criticality numbers on a criticality matrix like this, based on specific root cause statements or failure scenarios. So if you are with me, well done. Not many people would be after that trail of waffle. I see Johan says, can you set beta to 0 in instances where you'd expect that fatigue stresses will stay comfortably low below the endurance limit? That's not going to be incorporated with the beta parameter, because beta parameter says, well, if it does fail due to fatigue, what effect will that have on the system? Will that cause system failure? If you're going to have stresses below the endurance limit or the fatigue limit, then that would affect the likelihood of that particular failure scenario causing the failure of your rotary gear drive. And that's where your alpha parameter would be close to 0, / you might even discount that failure scenario entirely if you're confident it will never happen. Carl says that, put simply, criticality analysis compares the severity and frequency of failure modes on key assets and helps you prioritize maintenance tasks accordingly. When it's done correctly, it helps you improve your facilities productivity, reduce hazardous incidents, and streamline overhead costs. Any thoughts? That's just one interpretation of what a criticality analysis is. Like I said, in the standards, which mention criticality analysis, all they say is this is how you prioritize your failure scenarios. And you can see, I think writing what you wrote, Carl, just shows how many different ideas there are about what a criticality analysis is. So if you read the standard, it's all about you prioritizing failure modes where you don't need to use failure rates. So you can use subjective assessments. But a lot of people think, no, a criticality analysis involves failure rate estimates based on every single foreseeable way your thing can fail, which is then great for maintenance tasks. So on that note, there is a case to be made for having a good criticality analysis. But in practice, it's so tightly aligned with what a FMEA is perceived to be, things usually go wrong. And I'll show you why. Firstly, there is no such thing as a criticality analysis workshop. You just can't do it. You can't just sit there and brainstorm every single failure mode that's going to occur on a system yet to be designed and come up with meaningful estimates for the hazard rates, the alphas, and the beta parameters. So a criticality analysis must be something you incrementally build during production based on every failure mode as you learn about it after the corrective actions are implemented. So you cannot complete your criticality analysis until you've completed the design. And like I said, people believe that you have to use failure rates for most contemporary interpretations of what a criticality analysis is. It's all about predicting the effects of failure. So Carl and his friends can come up with those maintenance strategies, sparing and logistics, etc., etc., etc. Now, where can criticality analyses go wrong? Long story short, criticality analyses often go wrong where people pretend that this is not real. So criticality analyses often go wrong where people try and create a single FMECA workshop. Call this mistake number 2, where we say we're going to do criticality analysis as I've described as part of design. So we're going to have a single monstrous FMECA workshop up front where now, by definition, people believe we have to estimate the failure rate for every failure mode that's ever going to occur for something which is yet to be designed. And good luck doing that, which is why there's been a thriving reliability parts count prediction industry where, well, we feel pressure to do a FMECA up front before we design our things. So how do we get these failure rates? Well, we Google and use parts count predictions, Mill Handbook 217, et cetera, et cetera, et cetera. And we get these meaningless failure rates for failure mechanisms we don't even know will still be there by the end of our design process / missing failure mechanisms we haven't envisaged until they become apparent during testing, and it just becomes a mess. So for me, FMECAs, when they're interpreted as being something which has to have that criticality analysis done as part of the other FMEA parts, means you simply get a FMECA report with lots of failure rates. So much effort goes into it, we forget to do other stuff like updating during design, or missing unanticipated failure mechanisms, or prioritizing the vital few. It just is a mess when you try and do it this way. It just doesn't work. So when you do it this way, again, this is what your FMECAs start to look like. So criticality analysis, if you're serious about it and you're serious about the sort of the modern interpretation of what a criticality analysis is, has to be done separately and distinct to your system and design FMEAs. Now, after we've done that, then comes time for manufacturing, where the process FMEA, FMEA that Sanjeev asked about, can be conducted. So the process FMEA is usually completely separate to, you don't hear the term FMECA when we're doing process FMEAs very often, because process FMEA is a subject, or the object of what it is you're looking at is the manufacturing process itself. So the manufacturing and assembly process analysis with a focus on manufacturing related deficiencies. And again, your design FMEA will help you come up with the manufacturing specifics or specific specifications for your critical to quality parts and components. Now, this is how it's supposed to work, and you don't want to have manufacturing specifications poured over for every dimension of your components. It's just, again, the vital few. So your design FMEA team will say, look, this is our after we implemented our corrective actions, you still have weak points in your system. You'll never eliminate them. It's just that the weak points that are residual, very well, and you're comfortable that those weak points will cause failure well and truly after your warranty period or after your service life. In essence, how your smart lock's going to fail, when it's going to fail, and you're comfortable that because you know how and when it's going to fail for those residual weak parts, weak points after you've done a great FMEA process, those ways your thing are going to fail will be so far in the future that your product is now reliable enough to launch. And so a process FMEA will be based on those parts and things that were identified in design FMEA that the design team were concerned about not being high quality. So for example, if you need to have a very tight tolerance for something to work, then your design FMEA team will be the ones to come up with that, identify those tolerances, those specification limits to feed into a process FMEA. Of course, this only applies if the outcome is something like a smart lock. I've worked with organizations where they essentially only use process FMEAs because their products are things like toilet rolls. Toilet rolls aren't you wouldn't call them a machine, you wouldn't call them a system, you call them a product, but we're not going to pour over a toilet roll the same way we pour over a smart lock. And so a lot of organizations, manufacturing organizations, go straight to process FMEAs because all they want to do is work out how to quickly manufacture or produce toilet rolls to specifications. And you really don't need to subject a toilet roll to a design FMEA. So process FMEAs are very useful no matter what it is you're doing. And too many reliability engineers forget that no matter how much effort they put into testing, measuring, admiring the reliability of their designs, if they don't tell the manufacturing team what parts need to be toleranced to what level, you're going to have an unreliable product. So a process for me is all about making sure you have a really good manufacturing process. Great at helping you reach high volume manufacturing really quickly, great at minimizing downtime, great at minimizing scrap and rework, helps you, of course, with having high quality parts, helps you work out which components need to be subjected to statistical process control and PCA. Again, if everything's important, then nothing's important. So you only want to do SPC and PCA on parts that matter the most. So long story short, the outcome of a process FMEA is manufacturing process improvement. And hopefully this is starting to answer your question, Sanjeev, about when you do it. Now, what is a process? A process is a set of interrelated work activities that transform inputs into outputs. And for a manufacturing process, you're transforming raw materials or components into products. And a high quality manufacturing means limiting how far important characteristics are spread out. So if we go back to our smart lock, we might zoom into that keypad, which I mentioned, could be something that our system FMEA says, you know what, we know how to design good keypads. As long as our keypad is built within specifications, it's going to last for a long time. We don't need to do a design FMEA. That means we need to make sure that our keypads are built to specification. We know that our keypads are essentially going to be used in a way where users or customers are going to push keys with a certain force. And as you're pushing the key on a smart lock or a phone or anything else, your fingers experience what's called a peak force before the key starts to really start moving all the way back until it's gone through what we call the stroke. The travel of the stroke is how far your key goes before it makes contact with the PCB behind it. Then you'll experience a sharp increase in force, letting your finger know you have arrived, and then you go back as you pull your finger out. So that stroke is very important because it needs to be more than 0.8 millimeters to feel good, and the peak force needs to be around 0.12 newtons to feel good. It should be less than 0.12 newtons to feel good. So we know what we need to have in terms of customer experience with our keypad. So what does that mean for a manufacturing process? Well, if we zoom into our key, in this case, key number 2, we do a cross section. This is our silicone keypad. You can see the stroke is the difference between the pad and the PCB behind it. So remember, we want it to be more than 0.8 millimeters, but we also know that if it's greater than 1.5 millimeters, i.e. that you have to push the key a long way, our keypads wear out quickly. And so a design FMEA would ideally identify that we need to have the stroke of our keypad between 0.8 and 1.5 millimeters if you are going to do a design FMEA on the keypad. But if you are confident that we know keypads well enough that this characteristic is ubiquitous, it's don't have to research it. If we just know this, and to be fair, most people who design keypads do know this, then you might not need a design FMEA. But either way, you get a specification like this. The stroke needs to be between 0.8 and 1.5 millimeters. So a process FMEA is all about making sure we get that characteristic right along with everything else. So you can see there's tons of other different characteristics for our keypad dimensions, but these aren't important, or at least part of the vital few that influence reliability. They just need to be about right, but not really accurate per se. The stroke is what's the most important thing. Of course, there's key clearance as well, where you can see there's a space between the key and the metal faceplate. And so we need to make sure that the key is not super close to the metal faceplate, otherwise it might rub. And that means even though the keypad is built or manufactured beautifully, we need to make sure that it doesn't rub against the keypad, or sorry, the faceplate, because when you rub against the faceplate, of course, it will fail early. And so this is all about manufacturing now. We want to make sure that our keypad is manufactured to high quality. These couple of very key characteristics are where they need to be. And so this is a process, more correctly, this is a diagram which represents the process of manufacturing a silicon keypad. And we're not going to go into each one of these things right now, but you can hopefully see we have a process flow, and we have different activities as we go through turning our silicone ingredients and vulcanizing agent into a beautiful final product. And the process for me is going to pull apart every single step of this process and work out where it could go wrong, and making sure that in advance we have the safeguards, those fast, simple, free safeguards to make sure our keypad is manufactured to a high quality. So that's here endeth my conversation about FMEAs and FMECAs. And I suppose the last little bit was all about process FMEAs, and hopefully that answered a couple of questions. Before I open it to more questions, I can see that Carl writes, any planned obsolescence, any thoughts? That's a topic which is outside today's webinar, but in terms of what we're trying to talk about in FMEAs and FMECAs, there's lots of other webinars we talk about that, so I'm going to press pause on that one. Nasri writes, any thoughts on calculating criticality through multiplying severity, occurrence, and detection, each one assigned 1 to 10 grades? So what you're talking about, Nasri, is a risk prioritization number that many FMEA practitioners use. And again, technically, that is also a criticality number, although in practice, many people make the distinction between an RPN, the way you describe, Nasri, and a criticality number, the way I described in this lesson. Technically, the standards say they're one and the same thing, because you can choose whatever metric you want to use to prioritize failure modes. And so by definition, if you're going to call that a criticality analysis, whatever method you come up with, including just essentially different colors, where red is bad and green is not so bad, that is a criticality analysis. So technically, yes, you can call whatever number you use to prioritize failure modes a criticality number. But again, in practice, many people believe passionately that a criticality number is the number I calculated for that rotary gear drive. Samantha asks, what's the difference between a system FMEA and a functional FMEA? Great question, and that will take a little while to answer. But a function FMEA, you could argue, is, well, not you could argue, where a system FMEA is very, it works with a design FMEA, and it's very subsystem component centric. So you look at, okay, how can my system not work, and what components are going to sort of keep me up at night? A functional FMEA, instead of looking at components and per se, is it looks at the how your thing provides a particular service. So, for example, I was working with an organization manufacturing plasma cutters, and as opposed to looking at components, we looked at the process of how those components interact to create an arc. And so we had capacitors do this, power supplies do that, and then transfers into this and that. And so instead of looking at components, you create with you create essentially a functional diagram which explains how you create that arc that cuts through metal. And so it's a little bit philosophically different, very, very useful. And I think most organizations tend to need to pick which approach they want to use and embed in their culture. But without saying one's better than the other, they just have different characteristics. And hopefully that sort of answers at least some of your questions. Now, thank you, Nasri. Thank you, Carl. Thanks, David. Any more questions or comments or doubtful points? And remembering that there is an accompanying workbook, which Fred has shared in the chat window. I think my key takeaway too is that a FMEA / FMECA, whatever you want to call it, it's there primarily to make your design or process better. Criticality analyses, as modernly interpreted, tend to take away the focus from improving design and processes to filling in a huge spreadsheet with failure rates. That's a tragedy. Of course, there is a time for certain organizations to have to get that table of failure rates or hazard rates, but too many times we simply force that into what should be a reliability-centric activity, and we just simply spend time having a bunch of people sitting around tables, guessing failure rates, putting it into a spreadsheet, and then going home very tired. Ken, just off topic, the CRE exam prep course is still no, as of right now, it be closed. If you want to register for future CRE courses, just please let me know. Samantha writes, how do we deal with faults that could result in multiple failure mechanisms? So that would be how that would happen. How that would work, Samantha, is as opposed to you having faults that result in different failure mechanisms or looking at it in that way. Let me go back to this slide here where I have this sort of segmented pie chart. What would happen is that we know this outside little slice, ring of slices is where the faults occur. If you have one fault that could result in different failure mechanisms, what would happen is you'd have perhaps this slice over here, which I'm circling, and this slice over here, which I'm also circling, and this slice over here, which I'm also circling, perhaps being the same fault. And you can see how that same fault is now represented in 3 different failure scenarios. Does that answer the question, Samantha? No worries. Thank you, Andre and Julie and Sanjeev. Any more questions, comments, doubtful points? It's just crazy how this very formalized approach to criticality analysis is now seen as the textbook definition of criticality analysis, where criticality analysis is technically whatever way you use to prioritize the things that are going to keep you up at night. Thanks, Kenneth and Johan. Keep up. Thank you, Michael and Ken. I think we're running out of questions, Fred. Could be wrong.